When you analyze a rational function, this is a function made up of a numerator and denominator of algebraic terms. You can have numbers and or letters for a numerator and denominator. In your homework set, you're going to be asked to give the domain of the rational function, identify any vertical asymptotes and horizontal asymptotes. As far as domain goes, that just means the set of all x values that your function will take, calculate, and produce an answer. Sometimes you run the risk of dividing by 0 with a rational function. For example, in this one, if your denominator is ever equal to 0, for example, 2 plus 3x, there is a value of x that will make that denominator 0. Let's solve for that. Subtract 2 on both sides and divide by 3. Now, since that denominator is 0 when x is equal to negative 2/3, we're going to write that our domain is all numbers except negative 2/3. We do not want to use that value because that one creates a 0 denominator, which is undefined in mathematics. So your domain would be all real numbers except negative 2/3. Since our original function is not factorable on top and or bottom, 2 minus 5x, there's nothing to factor out. 2 plus 3x, there's nothing to factor out. If that's the case, where your denominator is not factored and cancels with any common factor in the numerator, your vertical asymptote is actually the value that you're throwing out of the domain. For this one, it is x equals negative 2/3. Now we're going to look at an example in a little bit where it's possible through factoring and canceling to remove your denominator, and then you may not have a vertical asymptote at all. Let's also think about, after we identify horizontal asymptote, what vertical and horizontal asymptotes look like on the graph of one of these rational functions. When you're asked to identify a horizontal asymptote of a rational function, we're going to take a different approach. Vertical asymptote, you identify the value or values of x that create a 0 denominator, and the denominator cannot be removed by factoring and canceling. Horizontal asymptote is going to be the value that your graph flattens out at on the far ends. In other words, when x is really large or really small, we want to know if there's a certain y value where the graph flattens out. The easiest way for me to tell you to identify an horizontal asymptote is to take the most dominant terms from your numerator and denominator. In this particular function, the most dominant term from the numerator is negative 5x. The most dominant term from the denominator is 3x. Since both x's are an understood power of 1 and they're equal, your horizontal asymptote is going to be y equals negative 5/3. So if you were to take a really large value of x and substitute it into your function, your final answer would be something really close to negative 5/3. How does all this play together when you draw the graph of a rational function? Let me draw some x and y axes. The vertical asymptote was at negative 2/3. X equals negative 2/3. That's going to create an invisible barrier where your graph will never be equal to negative 2/3. Your function is undefined at that x value. Your horizontal asymptote is negative 5/3. Y equals negative 5/3. Whoops. I went positive instead of negative down here. Now your graph can cross a horizontal asymptote. It just won't cross a vertical asymptote. If you take your graphing calculator and generate the graph of this function, I'm going to complete some of these asymptotes. There we go. Okay. What you'll find is your graph will hug the horizontal asymptote on the far left and right ends. Never touching or crossing the red vertical asymptote, but hugging the blue horizontal asymptote. And a lot of times, if you think of trying to put two magnets together with the same poles facing each other, how they repel one another, that's kind of like a vertical asymptote. Let's quickly do a second example. This one's a much simpler rational function. First, let's identify domain. Domain is all the good x's you could plug into this function. Now, if you look at your denominator, what value of x would make it 0? That's right. x4 would be equal to 4. Now, since you don't want a 0 denominator, your domain is all values of x. I'm just going to write it instead of the interval notation like the last example. All x values except 4. That's just an informal way to write it. If you're ever asked to write set notation, all values of x such that x isn't 4. These are all different ways to write the same thing. The vertical asymptote, since x minus 4 doesn't have anything in the numerator to cancel, x equals 4 is your vertical asymptote. It's actually the value that you throw out of the domain. Horizontal asymptote. For horizontal asymptote, remember that we compare the dominant terms from top and bottom. This one, there is no x in the numerator. There is an x in the denominator. So I'm going to recopy the function. Also think about this. Horizontal asymptotes, if there are any, occur when x gets really large. Well, if your numerator is always stuck at 3, but your denominator keeps getting larger and larger, think of it this way. 3/5 and then 3/7. The bottom gets larger, but the value of the fraction gets smaller. 3/10 is smaller. 3/20 is even smaller. But what you look for is if you don't have matching dominant terms, like the last slide, we just use the coefficients from each of those x's. But if you have a fixed numerator with a growing denominator, your horizontal asymptote will always be 0. If you grab your graphing calculator and put the function in, just type it into your y equals screen. A horizontal asymptote of 0 just means the x-axis. Y is equal to 0 on the x-axis. The vertical asymptote was at 4. And so there's that imaginary border that your graph never crosses. Okay, so if we go to our y equals screen and we graph 3 over x minus 4, then we get a graph that hugs the x-axis. The bottom drops out on this side of the vertical asymptote. Then the graph appears way up here, and then it flattens out at the horizontal asymptote. And so like the first example, you have a broken graph that diverges from itself at the vertical asymptote, but flattens out at the horizontal asymptote.